Okay, hello and welcome everyone to this lunchtime seminar. My name is Mohamed Elzeadani, and I chair the Young Members Subcommittee of the Society for Earthquake and Civil Engineering Dynamics. I'm delighted to have with us today three speakers, Ahsana, Mauritz, and Şahin, who each will be sharing with us insights from field missions they've been involved with. I also must say that this is probably the first event that we co-organize with both EFIT and the ISROC Midland counties. So many thanks to both Sarah and Alfred for all their efforts in putting this event together. So just a few points before we begin. Please keep your video cameras off and microphones on mute for the duration of the presentation. Also, please note that there will be a Q&A session at the end of the presentation. But if you have any questions in the meantime, then feel free to drop them in the chat. Also, please note that this session is being recorded and will be uploaded to our SECID YouTube channel. Therefore, by joining the call, you consent that any views or information you share will be made public. Just a few announcements, mainly for our SECID members. We'll be organizing a site visit to Servotest on the 11th of June. Servotest is a UK-based supplier of hydraulic actuators and shaking tables for dynamic and seismic testing and simulation. So we'll be visiting their facilities in Egham. And this is free to all SECID members, and registration is limited to 30 people. I will drop the event webpage in the chat soon. So if you are available on that day, then please do check it out and consider joining the site visit. And one more announcement, our annual SECID Fund Award will be opening soon on the 1st of June. So this is an award of £1,500, and it's intended for individuals or teams who seek to further their studies, research, or career in the field of engineering dynamics. And it's again open to all SECID members. And further information on this will be circulated to members. So do keep an eye out for this. And if you work in this space, then do consider applying as well. So I pass over to my co-chair, Sarah, to introduce our speakers for today. Thank you.
Thank you so much. I'll just go ahead and present our speakers in the order in which they should be presenting in. So first we have Dr. Ahsana Parammal Vatteri. Ahsana is a postdoctoral research fellow at the UNESCO Chair, where she focuses on developing tools for disaster resilience of integrated systems, particularly the application of Bayesian networks and agent-based modeling for system resilience problems. She focuses on confined masonry typology of buildings, especially school buildings, and the resilience of education and associated critical infrastructure. Ahsana also acts as a module coordinator for undergraduate and postgraduate modules at UCL. Her other engagements include post-earthquake reconnaissance missions, taxonomy development for confined masonry school buildings. This was used for the GPSS project for the World Bank. Consultancy projects on seismic safety assessment of schools, and delivering capacity building workshops and online courses. Our second talk will be given by Mauritz Feldbrugge, who holds a BSc and MSc from Delft University of Technology, specializing in geoengineering and remote sensing. He is currently a research associate at the Earth Observatory of Singapore, where he focuses on producing damage and flood proxy maps for emergency responders and humanitarian organizations. Mauritz is passionate about bridging the gap between academic research and real-world disaster impact. Our last talk will be given by Şahin Dede, who is a structural engineer with a specialization in extreme loadings. Presently, Şahin is a PhD candidate at University College London, investigating the multi-hazard vulnerability of tunnel-formed buildings to earthquake and fire hazards by integrating sophisticated numerical modeling, post-earthquake field assessments, and computational programming. His research experience also spans seismic design and assessment, real-time earthquake loss mapping, and catastrophe risk modeling. So if I could hand over now to Ahsana to get us started on the first talk.
Hi, thank you, Sarah, and thank you, Mohamed, for the invitation and kind introduction. I understand this is a very quick session, so I'll just get started on. Let me share the screen. I hope you can see the screen well.
Yes, we can see it,
Yeah.
Ahsana.
Okay. So yeah, good morning, good afternoon, everybody, and thanks for joining this session. I am a research fellow at University College London, as Sarah introduced. I work with the UNESCO Chair in Disaster Risk Reduction and Resilience Engineering. So in this presentation, I'm just going to provide a few of my reflections based on my experience working on remote and field earthquake reconnaissance missions. So this is based on the AGNC mission in 2020 and the Turkey mission in 2024. For the rest of the presentation, I think this is going to be almost like a comparison between the two, but my colleague Şahin will be presenting a bit more on the Turkey mission, so I will omit the details and leave it for him. So this agency earthquake and tsunami, this happened on 20th of December 2020 at the peak of COVID, a magnitude of 6.9. Affecting these areas in the Aegean coast of Turkey and the Samos Islands in Greece. Also triggered a tsunami up to 2 meters, and this was hence a complex mission. It was covering a wide geographical area, and also two hazards and the after effects of that resulted in 117 casualties in Turkey and 2 in Greece. One of them in Turkey was from the tsunami. And you can see the cost implications as well. With the Turkey mission, again, it was much larger in scale. It was affecting the parts of Turkey and the northern Syria, over 50,000 casualties in Turkey alone, affecting 11 major cities in Turkey and northern Syria. Again, we have more than 8,000 casualties, but we were mostly focusing the mission only on Turkey. With the hybrid both of these missions were hybrid reconnaissance missions. So as I mentioned, the 2020 Asian earthquake occurred during COVID pandemic, and due to these travel restrictions, we really had to explore other options, other opportunities to have an effective mission. So this was inspired also by the 2020 Zagreb mission, which was remote. Hence a hybrid approach was adopted for the Aegean mission. And the mission was led by Yasemin. It was a team of about 24 people, mostly desk-based analysis of open source information and ministry data, but also 4 of the members actually collecting data from the field. It was mostly like a remotely managed field assessment. And here we had several teams working together between seismotectonics, geotechnics, structures, and relief and response recovery as well. With the Turkey mission, it was much larger in scale, similar to the event itself, and it was a larger team of 30, about 50-50 split between field and remote team. So lessons from obviously the 2020 mission actually guided the 2023 mission, where different teams were working together before going to the field and during and after the field mission. So here we also had some available information from the ministry, for example, guiding which they have already done a certain level of damage assessment, a very rapid one, to highlight areas of severe damage. So in terms of data collection, in the agency mission, we were very much focusing and concentrating our efforts on reports, also issuing public surveys to gather information and producing mission blogs, along with assessing field collected data from other sources. And we also applied this EFIT mobile app, which was done by 4 members who are local to the region, 2 in Turkey and 2 in Greece, in Samos, which was very well managed through this EFIT learning from earthquake app. So what it does is it sends their collection of information in terms of pictures and damage assessment at varying grades to a repository where we can access that and perform secondary assessment on the damaged data. In addition, we also had some social media analysis where the responses of people posting on platforms like the last Quake and the Twitter were analyzed for any quantitative measures of understanding the intensity of these events. And in this Turkey mission, again, we started with remote work for the week or two. Before going to the site, we heavily concentrated on available data and also assisted by a team dedicated on remote sensing. So this actually helped us to form this itinerary for a field work. The first field trip was with about 15 members going for a week in March. But again, part of this team continued to go and collect data in subsequent field trips. So once we then collect the data, we conducted detailed damage assessment, categorizing buildings of different typologies into different damage grades. So this was done at different levels. So we did a primary data collection, as we said, by the field crew, but then we conducted a secondary damage assessment on that data. And in addition to that, we also did a primary assessment on additional pictures they had gathered from the field. So where they didn't have enough time and resources to do the damage assessment. In addition to that, Turkey Ministry had already done a quick damage assessment and uploaded a wealth of information and database. So that was our other source of data to actually go and collect, do the damage assessment. So in this case, we were given pictures of buildings from different angles, mostly only from the exterior because they were not allowed to go inside, also considering the COVID pandemic. In the Turkey mission, we did both the review of damage from existing literature databases, and the field damage assessment. So we had a focus on this rural and urban context. So rural context often gets neglected at the time in the existing literature and the work. So that was one of our focus, and also this traditional and modern construction and how they fared in this earthquake. So because Turkey mission will be covered by Şahin later on, I will just give a bit more updates on the Aegean Sea mission. As you can see here, we looked at RC typology in detail, where we had some heavy collapses, complete collapses in a very limited area in Izmir in Turkey, which was the center of most of the casualties as well. We also looked at masonry buildings with varying damage states from both Turkey and Samos. And in addition to that, we had some focused efforts on the traditional buildings. And in this mission, we also had the tsunami, as I mentioned before. So team was focusing on assessing what is the impact, how do we actually categorize this damage, because this is relatively new, and even the IFIT LFE app was updated to incorporate these additional requirements. So the observation was that the tsunami was not causing structural damage. It was observable in terms of watermarks, but also heavy damage on content and boats in the port. So overall, we then categorized into the damage distributions. In Turkey, it was very obvious that this damage was concentrated in 2 districts, as I mentioned. And it was partly due to the site issues, but again, we saw buildings which were sitting in the same site, but one collapsing and one surviving. So this was also issues with non-compliant design, workmanship, and modifications after the buildings was constructed, and so on. And in Samos, we looked at damage which was much more distributed, and also the building stock and the population was very, very different from Turkey's situation. So this was aged and poorly maintained, mostly masonry kind of construction. And we came across a lot of abandoned buildings and low population density. Overall, I think we noticed a few things that really worked well. So effective communication between remote and field teams, that was the critical element. This kind of preparatory work before going into the field, and sufficient training to use the app was another very effective factor that helped. And having local field crew in the team and to cross that barrier of language and culture and who are familiar with the situation, that really helps things to pick up the speed. And it is also challenging in the sense that if we are aiming for a completely remote mission, it is challenging to get useful, reliable data. So there is a lot of data, but it may not be sufficient to do a full damage assessment. And again, it depends very much on country, the dispersion of damage, as I mentioned in the case of Turkey and Samos. And it's often incomplete and uncertain. So as a PhD student and a postdoctoral fellow during these missions, I wish I would just share my background and learning. So I was fortunate to be part of these, and I thank UNESCO Chair and EFIT for this opportunity to be part of the mission. So this was, I was contributing mainly as a remote data collector and damage analyst. And my background in structural engineering and earthquake engineering really helped. And also my specific interest in masonry and confined masonry was a bonus. So we were coming up across a lot of masonry buildings, which was of my particular interest. And in Turkey mission, I was already a postdoctoral researcher, and it was adding to a bit more of responsibilities than the first one. And I was working in 3 teams this time: the structures, infrastructure, and the RRR, the relief, response, and recovery. So, and also assisting both the remote and the field missions. And by this time, I was working more on the education infrastructure. So I focused my efforts also on data collection and damage disruption assessment of schools and healthcare facilities. So it's either damaged or it's not damaged, but used for other purposes, which again then disrupts its primary purpose. So as just to conclude my learning experience, this has been, the Asian mission has been probably my first experience working in such a large collaborative environment where there are several workflows and this information and coordination between teams that has to all work so smoothly to get any work done. So this was my first introduction to these things, and it was a learning experience. And you learn to deal with uncertain data and make decisions with what is available. And with this data gathered, we actually then went on to develop some empirical fragility functions as well. With Turkey mission, it's an entirely different game. You are faced with this logistics of a field mission, preparations and health and safety, for example, the asbestos scare, and then this ground reality. So nothing really prepares for you until your first mission, I think. So you come across situations with how people are living in a post-crisis situation, how systems are still functioning despite such large-scale devastation, like the limited facilities, temporary settings, like the field hospital you see here, tent camps, and how the real impact of seismic engineering actually saves lives. So for example, this hospital we visited with base isolators, this actually did not suffer any damage, and it acted as a shelter and a directly operational hospital during the whole time. Similarly, how retrofitting saves buildings and lives. So these buildings you see here, these two were retrofitted, but there was a third building in the empty space which was completely collapsed. You also interact with people in crisis, how life goes on after such an event. We see a lot of community effort to bring people together, to help with mental trauma, also to distribute aid and food, resume education, and so on. So overall, I think it is a very impactful event in your life as such, as a researcher going into field. I think maybe people with several mission experience might get used to it at some point, but yeah, for me it was really an eye-opening experience. So this is Antakya in Turkey after the 2023 mission, before and after. So I remember the day we visited Antakya, and it really stuck with everyone. Everybody was silent for that day because the scale of devastation was really, really high. But it's not all, we do have hope it's a team effort. It does bring with its own good moments and joy. So I think it comes with it's a full package. Thank you very much for your attention. I hope I've conveyed some useful points to you. Happy to answer any questions. Thank you.
I think we can move on to Mauritz. Thank you very much, Ahsana, for the presentation. And we can do the questions later towards the end as well.
All right. Thank you for the great presentation. Very interesting. Let me share my screen. Everyone can see my screen, question mark.
Yes, we can see it, Mauritz.
Okay, sweet. Yeah, first of all, thank you for having me here today. I'm very excited to share my experience as part of Team Landslides. Yeah, the point of this presentation is to just share my experience as Team Landslides, which was deployed as part of the EFIT Morocco mission. And without further ado, I will get straight into it. So, there we go. So for those of you that don't know, I know this is an EFIT and SECA talk. EFIT basically is an organization that deploys after major events worldwide, usually earthquakes. Usually the people that go into the field is a mix of academia and industry. Some of the past missions include Sumatra, Nepal, Albania, Haiti, and Turkey. So you can see they're quite productive in general. But today, as the title already says, I'm going to be talking about the Morocco earthquake, which occurred on the 8th of September 2023 and was a magnitude of 6.8, which resulted in roughly 3,000 fatalities, more than 50,000 homes destroyed, and billions of dollars lost. So it was a major event, which meant that it was a great opportunity again for EFIT to go into the field and basically learn from it, to make some observations with the goal of mitigating the impact of future events. Now, in this case, because it was Morocco, or the earthquake epicenter was in the High Atlas mountain range, we had two teams employed. One was Team Landslides, which, as you probably already know, is what I was part of. And the other one was Team Structures. We had two slightly different objectives. For us in Team Landslides, it was to map earthquake-induced landslides, and then Team Structures, which you can see on the right, they were looking at buildings instead. As you can see on the picture, we were a team of 6, although I'm only showing 4 because Martin and Darren were already gone at this point. We had our team lead, Mike, in the front. Then we have Marco, Keith, and then me. And then on the right, we have everyone that joined the field mission. If you pay close attention, you can see Sarah right there. But anyway, as I already said, that the main objective was to map landslides. If you look at the affiliations, you might notice that it's quite international. We had people from universities, we had people from industry, and then you had me. So I wanted to, before I tell you exactly what we did, which was basically a 2-part mission. First, before even going into the field, we wanted to remotely identify the landslides before going in the field and actually mapping them. I wanted to basically, you might be wondering, how did I end up in this team? So I wanted to give you a brief background on who I am. So for me, like Sarah already introduced, I did my bachelor at TU Delft in applied earth science, and then my master's in geoengineering. I always loved works. So for me, it was like a very natural progression from first mapping the geological units to then in my master's doing engineering rock units, and also like doing some slope stability. But it wasn't, or up until my master thesis, basically, I had a very linear path, which I was following the geotechnical path. But then like doing my master thesis, I happened to have been introduced to a remote sensing technique called INSAR. And as soon as I read that you can take millimeter accurate measurements from space, I've been absolutely fascinated from the technology. Still to this day, like I kept on working with it. But at the time, I was basically studying a slow moving landslide in Istanbul using this technique when the earthquake happened. And in the background, EFIT was already compiling the next field team. And then I got lucky because my supervisor, Georgia Gardina, happened to be part of the EFIT committee. And she knew that I really liked field work. So she asked if I wanted to apply to join the team. And I was like, of course, I said yes, because one, it was a great opportunity to learn from more experienced people in the field. Two, it was a project with real world impact. And three, I thought that I would be able to integrate this mission as part of my master thesis. Spoiler alert, that didn't really work out. But anyway, and at the time it was, I had, I guess, a unique background because I was trained geologically, but then I was introduced to remote sensing. So I was able to help both in the preparing of the mission, remotely identifying landslides, and then also help out in the field by mapping landslides. So as I already mentioned, it's two parts. So before we even went into the field, we wanted to know where the landslides are, because if you know where the landslides are, you can basically plan your route and be efficient while you are in the field. We use two techniques. One is called synthetic aperture radar, or SAR. And this one uses radar, which, as you can see on the animation, you basically have a satellite. The satellite shoots an electromagnetic beam, which upon reaching Earth's surface gets reflected. And then if you have, the reflection basically depends on many factors, but one of them is the electromagnetic properties. So you can imagine that if you have a grass field, for example, the reflection is going to be totally different than, for example, a rock. So based on these differences, you can analyze a large area with just one process, and ideally you are able to identify landslides immediately. And what I'm showing here is something called a SAR intensity map, where we basically compare the reflection before the earthquake with the reflection after the earthquake. And if we focus on the image, we cannot really identify any landslides. So you're not alone. This method didn't work out. And the reason why this method didn't work out is because the landslides ended up being quite small, roughly 10 meters, or smaller than 10 meters, and was mostly boulders. And the satellite that we used for this was Sentinel-1, which has a resolution of roughly 10 meters. So it wasn't sensitive enough to pick up on it. If it did work, you would expect to have nice white patches, and we don't see any of that. So instead, we had a backup tool, which is called optical imagery. Now, optical images are basically, they see the same thing that we see with our eyes. So what we did is we used a high resolution satellite from Maxar, which had a resolution of 30 centimeters. So it's quite high resolution. And then we divided our study area, as you can see here, into different blocks. And then each block or tile basically has a image before the earthquake and an image after the earthquake. And then we would manually inspect these very large areas to look for landslides. So this is what it actually looks like. On the left, we have an image taken before the earthquake, and then on the right, we have an image after the earthquake. And as you can see before, we just have some vegetation, and afterwards, there's clearly some movement in soil. So in this case, we would mark down the location, and then after having gone through all the tiles, we would compile something called a landslide inventory. So in this figure here, all the red dots are remotely identified landslides, which were mostly rock falls, but there were also some shallow translational failures. And with this, or as it says down here, we identified 464 landslides. And then with this, we were pretty much ready to go into the field, because then we could plan, okay, on day one, we want to take this route. On day two, we want to go there. And then it saves us a lot of time while we're in the field, so we can maximize, basically taking observations. So you might be wondering, what does one of these identified landslides actually look like in the field? Which brings me to my next slide. Here I have two figures. If we focus on the left one, in panel A, we have the pre-event optical image. Panel B, we have the post-event optical image. And then panel C represents the yellow dot with the view of what we actually saw in the field. So if we just look at the view, or if we look at panel C, this is what we see. But sorry, if we were to look at panel B first, all the arrows represent pre-identified boulders. So if we were to imagine that we're standing here, which is what we would see with panel C, we would see all the boulders compiled on the left. In this case, they were quite large. Some of the boulders were relatively small, but others, we saw boulders coming down the mountains that were the size of the cars, huge. But on the right, we have Keith for scale. We have one boulder that came down rolling down the mountain. And yeah, you might be wondering what determines the size of the boulders. Well, it's basically how much the rock has weathered, how many discontinuities it has, because discontinuities are just basically cracks. And then if you have some shaking, they start failing from there. But yeah, so this is just one example, but you might also be wondering, what did we do in the field? A typical day basically involved the night before we would plan our route, and then we would go from location to location and we would look at landslides. Here I have three images. If we focus on the left one first, this is a landslide. You might not really see it because my phone wasn't the best at the time. But what we did is we would make geomorphological sketches, which you can see on in the middle. So this geomorphological sketch represents the landslide that we're seeing. And then we take down different features, such as we see where the deposit is, where the source is, where we have different cliff lines, where we have a drainage line, and then we see that on one half of it, there's an older or a newer deposit. And this gives us clues. It gives us clues about what happened to this landslide, how stable it is. And we would pretty much do this for every landslide. And then if we were lucky enough, we actually walked up to the landslides with a geological hammer and we started doing rock mass assessments. We did the geological strength index, which basically just looks at the discontinuities and the weathering, noting down a few observations. But yeah, so we didn't just look at landslides for fun. We were there to actually make observations. And although our typical day involved tea for lunch, and we had a great time. Thanks to Mike, our team lead. He was really phenomenal at planning the whole thing. Overall, we mapped 2,671 landslides. And in general, considering that it was a pretty large earthquake, we've expected more landslides. We don't know for certain, but we believe it's because it's such an arid region. Lack of pore pressures probably contributed to the lack of rock slides. But then we also found out that the boulders or the rock falls depended on the lithology, depending on like what kind of rock. We had differently spaced joints. If they were closer together, we would have a smaller block. If they were like wider, we would have a bigger block. We also saw that they made a lot of road cuttings, for example, and by having these road cuttings, they actually destabilized the slope, causing even more slope failures. And even though they were relatively few, considering the event, they still had a large impact. They would still block all the roads. So we went, like almost a year, quite some time later. But at the time when the earthquake happened, all these rocks were on the roads. So that prevented help from coming in. So they still had a large impact. But yeah, since for me, I mean, what did I learn out of this? So for me, it was my first real world experience. It both gave me a lot of new skills, but it was also, it really solidified the passion for disaster response. Like the most obvious skill that I had to learn was geomorphological mapping. Believe it or not, but the sketch that I showed earlier was actually one of my better ones, or probably the best one. So you can only imagine the earlier ones. And then I also learned that SAR, or like the remote sensing technique that I was working on, has limitations. So initially I thought that like I could use my method to identify pre-identify some certain areas that were already moving that are more likely to fail during the earthquake, kind of like a susceptibility map. But because my method measures the deformation slowly over time, and it's usually related to like ductile or soils that are like slowly deforming. When it comes to rocks that are just like stable, then unstable, it decorrelates is what we call it, and that we don't have any measurements. And then third, this experience really, like I already said, solidified my passion, and it led me to be where I am now. So now, as Sarah already said, I'm in Singapore as part of the Earth Observatory, and they call me mission controller. I'm responsible for producing both damage and flood maps. Here we have like one of those damage maps, and I basically respond to all kinds of events in Southeast Asia, which is really meaningful. And then I suppose on the practical side, if you ever are in Morocco and a wholesome villager gives you an apple, make sure to peel it, because you might up with food poisoning, which happened to me. But it happened on the final day when we were on the way home. So at that point, the mission was already over and it wasn't as bad. So with that, I welcome any questions in the future. can also contact me anytime if you're more curious or if you want to know more details. So thank you.
Thank you very much, Mauritz. And I'll watch out for apples if I ever end up going to Morocco.
Yeah, please do.
Pass over to Şahin for the final presentation, and then we can have Q&A.
Yeah. Yeah, first of all, I would like to thank the Young Members Subcommittee for organizing this brilliant event and for their invitation. I also would like to thank Ahsana and Mauritz for their very interesting and valuable presentations. So in my presentation, I will rather follow a different perspective than Ahsana and Mauritz, as they already provided quite a lot of technical and practical aspects of the field missions. So in my presentations, I will try to strike a balance between the technical and practical content and my own experiences and conclusions and reflections as an early career researcher through the lessons that we can take for our future career. What I share in my presentation draws on 4 different field missions, all of them focusing on the February 2023 earthquake, and they were carried out at different times over an extended period, starting from the 3rd week following the earthquake and up to the 16th month following the earthquakes in February 2023. And before turning to those experiences and reflections, I would like to briefly introduce myself so I can provide you with the perspective I'm speaking from. And from there, I will move to my own conclusions and share what the field has told us as engineers, or to say my interpretation on what the field told us. I should specifically focus on my previous experiences so I can provide the perspective adequately. I'm a civil engineer from my bachelor's, and then I studied master's in earthquake engineering. During my master's, I have also worked as a at a research role in the same department and worked on different parts of the earthquake engineering, but mainly focusing on the structural earthquake engineering part. So seismic design and assessment, urban risk and loss assessment, seismic damage assessment, based on remote missions during that time, were the main experiences that I had acquired. So I can describe myself as a more structural leaning earthquake engineer. And following my master's, I started my PhD in civil engineering at University College London. And during my PhD, as Sarah kindly summarized, I worked on advanced finite element modeling, seismic fragility analysis, seismic damage assessment, again, this time both remote and on-site. So it would be good to, refresh our memory again, although Ahsana briefly mentioned the key aspects of the earthquake that occurred in 2023. On February 6, in midnight, an earthquake with moment magnitude 7.7 with a focal depth of 10 kilometers struck the southeastern region of Turkey. So the epicenter of that earthquake was near the border between Gaziantep and Hatay, the provincial border between the Gaziantep and Hatay. And the fault was, the ruptured segment of the fault was almost 300 kilometers. So the scale was just extraordinary. And almost 9 hours later, there was the second main shock. It was 7.6 in moment magnitude, and it this time impacted the eastern part of the country. But as you can see from the map on the slide, there was a large area that these 2 earthquakes heavily impacted. And this was something also, another unusual or not so considered aspect of the earthquake, because the seismic design guidelines focus on a single main shock. But in this case, we experienced two really large earthquakes happening within somewhat near vicinity, and they were followed by strong aftershocks reaching up to 6.6 magnitudes in the following 2-3 weeks. So there wasn't enough time to recover for the people who were impacted by the earthquakes. As Ahsana mentioned, 11 cities where an estimated 14 million people resided before the events, and those 11 cities were declared the disaster region. These events claimed the highest number of casualties in the country's history, unfortunately more than 50,000 people. And the comprehensive damage assessment conducted by the relevant ministry have showed that more than 500,000 houses were either severely damaged, collapsed, or required urgent demolition. So the scenery on the field was just very heavy to take in. As you can see in the image that I'm sharing, which I took in my first field mission, that the feeling and the scenery was something that you wish it wasn't real, because there were regions, specifically Antakya and also Islahiye, that you were just looking around and there wasn't a single building that were standing. So this particular field mission took place almost immediately after the rescue missions ended. So the primary importance, the crucial thing following the event is the rapid response and ongoing efforts of rescue missions. So we should have that buffer to deploy to the field, so we don't be a nuisance to the rescue mission operators and also rapid response officials. Therefore, we have waited for the rescue missions and then we were deployed on the site. The main focus of this first reconnaissance mission was Kahramanmaraş and Hatay. It was a team of 8 people that are organized by my previous department, Kandilli Observatory and Earthquake Research Institute at Boğaziçi University, that with my former colleagues and professors, that we went to most heavily impacted regions to understand, to have a holistic view of the damage, because as I showed in the previous map, that the extent was just immense. Therefore, if we preferred to have a holistic view of the earthquake's impact with such limited amount of people, we should have paid our focus to a localized area. And as Ahsana mentioned again, in Antakya was one of the locations that we observed the most worst or the uttermost destruction in the whole region. And through this field mission, we had the opportunity to understand, because there wasn't any debris removal or there wasn't the large-scale debris removal procedure started. So we understood how different infrastructures and lifelines and the urban environment as a system was impacted by the earthquakes. Following this mission, to continue on this mission, I should really state that there is no stronger reminder of the responsibility when you are deployed after a strong earthquake, when you see the disaster, when you see the damage and the consequences, then you realize the responsibility that we carry as engineers. It also provides a really strong perspective on how far the real conditions can be from the common engineering assumptions. And also, this field investigation has shown that a structure's performance cannot rest on guidelines alone, because I have observed, many of my colleagues observed, that although majority of the collapsed or heavily damaged structures were constructed before the moderate or high-level seismic guidelines, there were still some structures failed which were constructed after those guidelines were released or were enforced. And this is one of the cases which really shows that the dependence on the guidelines alone is not enough. A system's or a structure's performance is heavily depends on the correct application of methods at every stage, from design through implementation to final use. As you can see, this structure was not even under service loads, and it just collapsed, or partially collapsed, if you would prefer to call it. And again, concerning the use, that we designed the structure, that we constructed, but then if the relevant authorities doesn't follow up with what's happening with the use of the structure, then we can see a soft stir mechanism on the third floor of a structure, which was happened due to a column's cutting just to increase the space of the commercial entity on that floor, which resulted in the most adverse outcome. Following this field mission, I was involved in the longitudinal EFIT mission that Ahsana covered technical aspects and practical aspects. So I will just keep this part brief. This work was one of the most comprehensive field missions in the literature following the February 2023 earthquakes. And to learn from the disaster and understand the critical aspects of the causes of these consequences, this mission successfully combined different methods and perspectives, from on-site and remote damage assessments to social consequences, relief, recovery, and response efforts. Within this field mission, I worked at structures and relief response, relief, recovery, and reconstruction teams. Within the structures team, I had the chance to use my structural engineering skills in a sense to understand the differences between the on-site damage assessments and remote damage assessments. On-site, that you have the 3D feeling of the structure, and depending on the extent of the damage, you can have the access and investigate and examine the scale and the detail of the damage. But when you conduct this remotely, you may miss many of the significant aspects of the damage, specifically the internal damage, because most of the remote damage assessments relies on the external damage assessment, and there is this difference between these assessment results. But also, damage scales are quite qualitative protocols, which inevitably introduces the subjectivity to the assessment itself. So it was a really important exercise, and provides an understanding for the future use of the data when we are assessing, when we are appraising the damage, or when we are looking at the literature, because it provides us a really important information. I also worked on the examination of relief, recovery, and reconstruction, as I mentioned, because The engineering damage observed in the immediate aftermath represents only the initial stage of the loss process. But the majority of human, economic, and policy-related consequences accumulate over the subsequent months and years. Therefore, understanding the relief, recovery, and reconstruction is one of the crucial aspects to understand the disaster. Following that, I was involved in a more focused examination, which was focused on a specific type of structures and was supported by EFIT as well. And the fundamental objective was to conduct an on-site examination of the response of tunnel from buildings, which is a specific type of reinforced concrete structures. As shown in the slide, these structures are distinguished by their structural system. They are characterized by having shear walls as almost only vertical elements. In many cases, the only vertical elements, and they were observed to perform better compared to other structures. So in this specific field mission, the primary objective was different than the others, as we paid all our attention to these kind of structures in the field, but also compared these structures with the other RC counterparts, other RC buildings. And these kind of detailed assessments also provide a means to calibrate and validate our finite element models. This is just a snapshot from my study that I'm showing, that how we utilized the field observations on a damaged existing structure in the field, and how did we use this calibrated numerical model to gain insights into the evaluation of damage. Although the earthquakes were occurred within a time period, we did not have the chance to understand the progress of damage between two different events. But when you use the field observations and when you calibrate and validate your numerical models, it means that you have a confidence in your model, and then you can test the situation that you cannot observe on the field to understand what has happened. Also, these kind of detailed damage assessments, which can take significant amount of time, allow you with the understanding concerning the parts where damage scales have drawbacks or shortcomings. So this exercise also led to proposing a bespoke damage scale for this specific type of structures, as we observed the common damage scales, EMS or FEMA, were lacking the specifications of the structure given here. And this field mission also provided us with the means to understand how the reconstruction efforts were happening, because this was almost 6 months after the earthquakes. And the last one was a different, again, another different set of objectives were followed. This was 16 months later from the events, and the primary objective was to introduce the new generation of engineers to the realities of a major seismic event, but also again to observe the state of reconstruction and how the normalization efforts, if it is possible, was moving forward.
Şahin, if we could, sorry to disturb you, if we could just wrap it up
Sure,
quickly so we can have time for question and answers there.
Yes, thank you. To reflect, I should say that based on my own experiences, a strong command of seismic guidelines and the ability to implement them correctly are essential, but was not enough on their own. We need to understand the foundational rationales behind those implementations, so that we can propose solutions to the situations that beyond the expectations of the guidelines. And also, the rigorous application of engineering ethics is equally important, because when we apply our knowledge, we need to ensure that we are moving with honesty and integrity and responsibility to society. And we need to ensure that we do all of these efforts in collaboration with all stakeholders, because engineering practice is not standing in isolation. We need to work with others and share our knowledge and share the risks, so the people who are taking these decisions can be aware of the problems, because earthquakes do not overlook any mistake or carelessness. And I believe this picture summarizes all what I was trying to say, as the only standing building here is the Chamber of Civil Engineering Association of the building of civil engineering chambers. Thank you very much, and sorry if I overgone of my presentation time.
Thank you, Şahin. I think I'll pass over to Alfred to moderate this Q&A session. And if you have any questions.
Fantastic. Thanks for that, Mohamed. Thanks, Ahsana, Mauritz, and Şahin for those insightful presentations. I'll now open up the floor for any question and answers. If you can put your questions in the chat, that will be appreciated. Thank you. Alternatively, I think, Mohamed, people can unmute and talk. Is that correct?
Yes.
Yeah. Okay.
Yeah, feel free as well to unmute yourself and turn on your camera as well. And while we do that, I could ask Mauritz a quick question. I was just thinking, because to check for the landslides where they happen, you need pictures before and then after the earthquake. So how regular are these pictures before the earthquakes are taken, and where do you get these pictures from?
That's a great question. So depending on the satellites, I think you're talking about the optical one that we ended up using. You have open source ones, which is from ESA, Sentinel-2. I believe that they take pictures don't quote me on this, but every like 10 days, something like that. But the problem with those is that the resolution is quite bad. It's open source, but the resolution isn't great. But the one that we ended up using is from Maxar, which is a private company, which is nice enough to provide these for free after major events occur. And I believe that their revisit time, because they have multiple satellites in orbit, so then the acquisition time decreases. I would say, again, I would have to look this up exactly, but between 5 days, roughly. But yeah, but then you have Planet, you have multiple companies out there. So in theory, you should be able to get a post-event acquisition within a couple of days.
Okay. Thank you.
You're welcome.
Got a question in the chat. And this comes from Alex Smith. And that is okay, I think it was about to.
It wasn't a question.
It wasn't a question. Okay. Yes, let's move on to Salah.
But I have another one which I can feed back with.
Go
How did you have much influence on the reconstruction effort? Because were they learning lessons from this and rebuilding better, or were the same construction methods creeping in as before? And that's quite a broad question, but did you get to feed back lessons learned from your research when they were rebuilding, or was the rebuilding effort happening too fast for you to impact? Or
would that be going to
Şahin? Yes.
Yep.
Thank you for your question, Alex. Yeah, it was moving really, really fast following the earthquake, because there was this immense rapid demand of housing concerning the scale, and the strategic way the government was followed was basically using tunnel front construction. So I forgot to mention that, but those structures are strategically important, as they are the predominant typology in mass housing projects. They are quick to construct, and they are, as I stated, perform superior than the other RC buildings. So they followed this strategy, following the observed better performance of the tunnel form buildings. That was one aspect. The other aspect is that following these sharings by the greater academic community, they introduced changes to the seismic design. So they will be also implemented in the new designs and new constructions. I hope this would answer your question.
Excellent. Yeah, no, thank you. And thank you everyone for your time on this. It's been brilliant. I must go now, I'm afraid. But thank you very much.
All right. Okay. Thank you. Yep. We have a question from Salah. So Salah is asking about, as a civil structural engineering student, what advice would you provide to someone who wants to learn about earthquake engineering? Also, most importantly, if the person wants to pursue a career option, what sort of knowledge should be acquired? An open question to all speakers.
Maybe Ahsana, I think, would.
I can start. I mean,
Yeah,
please feel free to add. No, this is what I have seen as I'm a civil engineer by bachelor and then a master's in structural engineering. But I came to the field of earthquake engineering through my research and then learning on the job kind of. So it's what I think is we get to that academic line of learning and problem solving is one part of that learning. When you're exposed to a real earthquake or an event of the scale, you start questioning your learning, the applications, and how well you actually understand things. So I think it's very good and very important to have that perspective beyond the books when we are taking up structural engineering or seismic engineering. And as we all mentioned in some of the cases, like you do see real impacts where engineering has worked and what has happened when it's not. So you are making an impact in reducing the risk, reducing the deaths in future events. So it is definitely a very rewarding career path to take in that aspect, I would think. That's all from me, please.
Yeah, okay, thanks. Hope that at least covers what Salah wanted to hear. I have another question. We have one in the chat, and this is probably 3 in 1. I'll probably start with the shortest one. It's a question from Ahsana. Ahsana, is there any reference to derived tsunami height?
I think the ones that I presented was from the observation. So they were CCTV cameras and the port structures had monitoring and so on. But if you look up literature from Tiziana Rossetto and the line of work she has conducted, where alongside Marco Baiguera, they have been leading that. Marco have been leading this part of the reconnaissance mission as well. So I'm sure there are also approaches to actually calculate the impact of the tsunami wave on your structure. So I mean, we have seen very much of this already codified and in your seismic design codes, but on the side of tsunami, it's still developing. So there is a lot of momentum. There's a lot of activities going on that side.
Thanks for that. Okay, another one from Car that is asking for INSA topic. How can we identify the artifault line? And also, does using INSA requiring license, and what is the satellite name that you are using?
I can answer this one. So for INSAR in general, there's a lot of people studying tectonics, so you can identify the active fault lines. It's not really my expertise, but I'm pretty sure if you know where the active fault lines is and you process time series, so you see like how much the different pixels have moved throughout time, you're able to see the movement. It's a little complicated because INSAR is always along the line of sight, but you can have like different satellites, combine them, and you end up with vertical and also horizontal displacements. But if you're interested, there are open source softwares. The most common one is called ICE. I will write this in the chat so then you don't have to remember that. And the data is all free. So what we use, or what I use most of the time, is from Sentinel-1, which is from ESA. And depending on the different bands, so like wavelengths, they have like different, what do you call it, limitations, for example. Yeah, so the most common one at the moment where you have the most amount of data is from Sentinel-1, but there's a new mission launching, NISAR, which has like a longer wavelength. So for my work, I'm interested in landslides. It's able to penetrate through vegetation, which otherwise is a problem. But yeah, and you can, I'll give you some references in the chat. I think that might be more useful. Thank you. I hope that answers your question.
Thanks for that. And we got third one from Carl. Again, is for the PGA contour map. I can see that it has 50% G. Is that possible to building surviving with that? And it goes on to also say that, and the other one, I need to probably try to paraphrase it. It goes on to talk about high building and the slenderness of the building as shown in the photograph. Is there an isolator being proposed? So PGA contour map, who is taking that?
I think I can answer that. I had used PGA contour map in my slide. So 50% G, yes, that's definitely possible to survive that. And there were structures that were survived, as I showed in the last couple of slides that I have used. The approach or the philosophy when it comes to high PGAs or high PGA is not a really good indicator of the damage, but when it comes to high ground motion demands on the structures, we rely on the inelastic response of the structures, the ductile response of the structures. So we expect the structures to exhibit some damage, but we definitely aim to control that damage so the functionality of the structure is preserved to a certain extent, but also life safety is definitely the utmost priority. But following these earthquakes also, these design philosophies and approaches were started to shape based on the observations as well. But yes, without isolator, it is possible to design structures that can survive these levels of earthquakes.
Okay, thank you very much. And I think that the bolt-on question to that has to do with some of the photos show high or tall buildings appear to be slender, and the question was, are they isolators incorporated within these buildings?
Not particularly in those buildings. Isolators in residential buildings in context of Turkey is emerging, but it's not as extensive as in, for example, in Japan. So these buildings, to my knowledge, were not isolated structures, but as I said, it's yet to emerge in Turkey. So those buildings were just designed following the code regulations and with strict implementation of the capacity design principles.
I think he was referring to the Toki buildings, Şahin. They do appear, yeah, the Toki. So the tube form construction.
I see. Yeah. Thank you for clarification, Ahsana. Those structures rely on shear walls and they have really long, in plan, their sections are really long. So they are really stiff structures and they tend to exhibit lower drift demand. So the damage is definitely constrained in those structures.
Fantastic. Thanks for that. I have one question here. With regard to the Tokyo earthquake, on reflection again, moving forward, what has happened in the country in terms of regulatory framework and again, strategies around robust design, construction regulations and compliance, etc. Has things moved on? And that might be for Şahin.
Okay, thank you, Alfred, for your question. So yes, as I briefly mentioned, following the observations and following the sharings of the greater academic and engineering community, there are changes to the seismic design guidelines. And also in the greater academic community, globally, there were discussions around the performance objectives that we impose to the structures because we aim to obtain life safety, but we have seen that there were many structures that provided life safety. There were no loss of lives, but infill walls were completely collapsed, leaving the structure as a bare frame. So lives are saved, but no one can live inside that building because there is no surrounding. And given the condition of on the site, no one has time and resources to rebuild the infill walls. So based on these observations and discussions, there is an update to the Turkish regulations which dictates a minimum amount of shear wall ratio. So implementation of shear walls will reduce the drifts and therefore will reduce the anticipated damage in the residential buildings. Before then, it was loose, but now it will be changing. So there is one aspect. And the other aspect, as I said, tunnel from buildings are strategic construction tools. And in the region, they were heavily, predominantly implemented as the new source of the housing for the people. I don't know if I mentioned the aspects that you asked.
Yeah. No, thanks for that. I don't think we've got any other question in the chat. If there's no further one, then I think it will be more of a closing remarks. So in closing, I would like to extend our sincere thanks to the three speakers for sharing such invaluable and insightful experiences with us today. We also want to thank all participants for their engagement and your contribution, and again, thoughtful discussions that has ensued as a result of the lectures. And special thanks will go to Mohamed and Sarah again for the coordinated effort that has gone into this to make this joint event, probably the first joint event across the three entities to come to fruition. And once finally, thanks to everyone for attending, and we look forward to having continued important conversations in the future. Thank you.
Thank you all. Thank you for having us, and enjoyed listening to you both, Şahin and Mauritz. Thank you, Alfred, Mohamed, Sarah. Thank you for this combined event. Look forward to speaking again soon.
Thank you for your invitation and interest. Thank you.
Hope to see you in the future. Bye-bye.